The idea of faster-than-light travel has long fueled the imaginations behind science fiction, captivating audiences with visions of interstellar voyages and journeys to distant galaxies. But in 1994, physicist Miguel Alcubierre took this concept from the realm of fantasy and brought it into the sphere of real science, sparking a wave of excitement and theoretical exploration. Inspired by the captivating stories of warp drives, a staple in science fiction, Alcubierre delved into the complexities of Einstein's general relativity and published a groundbreaking set of equations that described the possibility of a theoretical warp bubble, a localized distortion of spacetime. This bubble, according to his theory, would allow a ship to remain stationary inside, safely cocooned within its boundaries, while space itself contracted in front and expanded behind, effectively moving the ship faster than light, sidestepping the seemingly unbreakable cosmic speed limit. The concept electrified scientists across the globe, igniting a renewed sense of hope and possibility, as it remarkably didn't break any known laws of physics, offering a glimmer of hope that faster-than-light travel might not be entirely out of reach, but cleverly used the very rules of relativity to its advantage, bending spacetime in a controlled manner. Suddenly, the vast distances of interstellar space seemed less like an insurmountable barrier, and interstellar travel seemed less like a far-fetched fantasy, and more like a distant yet tantalizing possibility, a challenge to be met with ingenuity and scientific advancement. Yet, the Alcubierre warp drive theory was just that, a theoretical framework, a signpost pointing towards a potential path, but certainly not a detailed blueprint. Turning these complex equations into a tangible reality proved to be a daunting task, fraught with seemingly insurmountable challenges, opening up a Pandora's box of new questions and demanding a deeper understanding of the fundamental nature of space, time itself, and the immense amounts of energy required to manipulate space-time on such a grand scale. Decades later, the warp drive remains a tantalizing but speculative idea, a beacon of hope that continues to inspire scientists and engineers to push the boundaries of what we believe is possible. The Alcubierre drive's genius lies in its innovative approach to interstellar travel. It doesn't rely on conventional propulsion methods. It's in moving space itself, not the ship. The spacecraft remains stationary within a warp bubble. Imagine a surfer riding a wave, a perfect analogy for understanding this concept. The ship sits still, suspended within the warp bubble, as a space-time wave carries it across vast cosmic distances. The drive would contract space in front of the vessel, shortening the distance to the destination. Simultaneously, it would expand space behind it, creating a propulsive force. This coordinated contraction and expansion effectively pulls the destination closer to the ship. The ship's crew would feel no motion or acceleration, experiencing a normal environment within the bubble. Remarkably, the bubble itself could theoretically move faster than light, enabling faster-than-light travel. This seemingly violates Einstein's theory of relativity, but it doesn't. This is because general relativity states that spacetime itself can expand or contract at any speed, even exceeding the speed of light. Instead of relying on conventional rockets and propulsion systems, a warp ship would manipulate and warp the very fabric of reality itself. The challenge, the real hurdle. While general relativity allows for this concept in theory, providing a framework for its possibility, it doesn't provide a practical guide or blueprint on how to actually achieve it. Creating the required spacetime geometry, the precise warping of space, demands control over matter and energy far beyond our current technological capabilities. Most crucially, the biggest obstacle, it needs a bizarre ingredient, something that defies our everyday understanding of physics, negative energy, a concept that remains largely theoretical. Alcubierre's equations require negative mass or negative energy, a substance that repels gravity. This exotic matter would behave in ways never seen in nature. No evidence for negative mass exists, all known matter has positive mass. Quantum physics offers a glimmer of hope. Effects like the Casimir effect create tiny regions of negative energy. But these are minuscule, nowhere near enough to power a warp bubble. Engineering and containing enough negative energy for a spaceship is beyond imagination. Without this key ingredient, the warp drive remains a mathematical curiosity. Quantum tricks fall far short of fueling interstellar travel. 30 years of dedicated research into the Alcubierre drive have, unfortunately, only deepened the challenges we face. The initial promise has given way to a stark realization of the immense hurdles that stand in our way. Early theoretical models painted a picture requiring negative energy densities of truly astronomical proportions. We're talking about energy equal to the entire mass of Jupiter. A figure so large it defies comprehension. Subsequent tweaks and refinements to the model did manage to reduce this staggering requirement, but even these improvements only brought it down to the equivalent of a star's mass. This is still an impossibly huge amount of energy. No technology that we can currently conceive of, or even foresee in the near future, could ever hope to harness and control such an immense energy source. The engineering challenges are simply insurmountable with our present understanding. Worse still, the very structure of the warp bubble itself may be fundamentally and fatally unstable. This instability poses a significant threat to its viability. It's highly likely that the bubble would self-destruct almost instantaneously due to the unpredictable and often destructive nature of quantum effects at such extreme scales. Even if we were to overcome the energy and stability problems through further theoretical improvements, the warp bubble would probably tear itself apart long before it could successfully transport a ship across any significant distance. Despite all these daunting obstacles, the Alcubierre drive remains a beautiful and elegant idea, a testament to human ingenuity and our relentless pursuit of the seemingly impossible. But for the foreseeable future, it is simply not a practical or feasible path to the stars. The universe, it seems, is not yet ready to yield its secrets so easily. It continues to inspire countless works of science fiction, fueling our imagination and driving us to dream of a future where interstellar travel is a reality. And perhaps more importantly, it serves as a valuable tool for physicists, pushing the boundaries of our understanding and helping us to probe the very limits of Einstein's theory of relativity. So, for now, the dream of interstellar travel will have to remain just that, a dream. We must wait patiently. We await a scientific breakthrough, a paradigm shift, something that transcends even our wildest and most imaginative theories. The universe may yet surprise us.